All right, welcome back to our second last lesson here of this unit and the second last lesson of all of Chem 30. So this one right here, we're going to be looking at base strength and the ionization constant for a base, which is going to be labeled Kb. Basically the equilibrium constant for a base. Now, we've already done some work in the past where we had a look at strong bases. Of course, we knew strong bases were ionic hydroxides that dissociate to produce hydroxide ion. And of course, we found the concentration of hydroxide ions from using the dissociation equation and the mole ratio, right? So we did this. So you can go back to last week when we were looking at pH and pOH calculations only for strong bases doing this. And then, of course, even for Chem 20, this is what we really focused on. So for example, like we have just two examples here, the sodium hydroxide solution and the barium hydroxide solution, where first you needed to write out your dissociation equation. And then remember we did concentration of hydroxide was equal to the concentration of the base times our mole ratio. So in this case right here, it was 0.0100. The mole ratio was 1/1. And then we can get the pOH is equal to negative log concentration of hydroxide. And we get something like this. Right, so this was kind of nothing new, and we done this there last week. Now, of course, you needed to remember this whole mole ratio thing because if you're given something like barium hydroxide, where the dissociation equation is just a little different, because in this example right here, the barium hydroxide would dissociate to get barium 2 plus and 2 hydroxide molecules. So when we did the concentration of hydroxide is equal to the concentration of the base times our mole ratio. In this case, it was 0.10 times 2/1, wanted over given. To get that. And then, of course, pOH is equal to negative log concentration of hydroxide, which was 0.20, and we get a pOH of 0.70. So this was all done last week, and this is all of our Chem 20 calculations on how to get pH and pOH of a strong base. Now, of course, in Chem 20 and even at the beginning of this unit, we didn't do any weak bases. Now, if you remember, and I kind of brought this up a little bit with our data booklet, is that this is the only strong base. Everything else above on our conjugate base side, these are all weak bases. So the gray OH minus, that's the only strong base. Everything else is weak. So we do have a list of a lot of weak bases. But one of the problems, you'll notice that there's no ionization constant for that base. It's all acid stuff. So we're going to get to that little problem now in a minute. So remember, a weak base is something that is a proton acceptor. It doesn't dissociate, it just accepts a proton. Now, weak bases only react partially with water, again, creating an equilibrium. So this is our general reaction for a base. Now, you will notice that we're using B minus for the general form. And the reason for that, same thing when you look at your data booklet, all of the bases are basically charged except for ammonia. That's the only one. All the other bases have a negative charge. Now, even though some of them has a -2 charge here, we're not going to put that in just to a general form because we're only showing the transfer of one hydrogen. So one hydrogen going from water to the weak base, producing our conjugate acid and our conjugate base. So when we're dealing with our base reactions, well, our equilibrium law, Oh, sorry, we're not doing equilibrium law yet. We're just going to show an actual practical example. So if we had the carbonate ion, so CO3 2 minus plus H2O liquid, we know that if this is the base, this is the acid, hydrogen goes this way, we get HCO3 minus and then plus our OH minus, conjugate acid and conjugate base. So, as kind of mentioned there before, and I almost jumped the gun on it, the Kb, or ionization constant of a base, isn't in our data booklet, so we will need to find it. And that's the problem we have highlighted down here. So for example, if we are given something that we know is a base, like sodium citrate. Now this is an ionic compound, so it's going to break apart into the sodium ion and the citrate ion. Which, if we look in our data booklet, citrate ion is right here. Now we will notice, so this comes from the hydrogen citrate losing its last acidic hydrogen, this right here, and forming this right here. You'll notice this is on the base section. This will act as a base and only a base. These hydrogens here are not acidic. The carboxylic acid functional group right here has no more hydrogens, so the acid functional group has no more acidic hydrogens. So it can only act as a base. Now this value right here, remember, these are all Ka values. So that's our first problem we need to overcome, and that how can we relate these Ka values into giving us something more tangible that we can use for Kb. And that is, of course, the problem we have right here. So first we need to figure out the relationship between Ka and Kb. Now we know the water has an ionization constant, and this is in your data booklets, is 1.0 times 10 to the power negative 14. Now, and we already know there is a relationship between acids and bases, where we already figured out if we multiply the concentration of both hydronium and hydroxide to get together, we get Kw. So this thought process of, okay, how can we relate Ka and Kb? Can we relate this to Ka, and can we relate this to Kb to get a new equation? Well, that's what we're going to figure out right here using this practical example. So this is just kind of proving how two of these are going to work. So if we write out, so we're going to use the acetic acid and hydrogen or acetate ion because these are both acids and conjugate bases of each other, and we're just going to work through this thought process of relating Ka and Kb. So if we start with acetic acid and we write out the equilibrium law, get the acetate ion and hydronium, we know Ka, the ionization constant for the acid will look something like this. Now, let's just say we do this for the acetate ion, which is a base. So if we wrote it the acetate ion, so CH3COO minus plus water. Well, now this is a base, the conjugate acid is CH3COOH, and we get OH minus. Now if we wrote it the equilibrium law, we will get something that looks like this. Now, for example, if we multiplied two of these together, because we already knew hydronium times hydroxide gives us Kw, so what happens if we actually multiply Ka times Kb together? Well, we substitute in our values. So Ka was CH3COO minus H3O plus all over CH3COOH, and our Kb was looks like this. Now, one thing you'll notice, some things are going to start canceling out, like the acetate ion, acetic acid. And what we are left with is hydronium times hydroxide. Just let me write this a little better here. Just can't really see that. What we're left with is just H3O plus OH minus, which is in turn KW. So, long story short, this is just proving that if we multiply the ionization constant by the ionization constant for the base, we can get KW. So therefore, we can use our acid-base table. All we need to do is identify its conjugate acid. So, let's have a look how this works. We can use this whole idea of Kb, and of course it's the same thing as when we looked at Ka, the ionization constant for the acid. That means bigger the value, the stronger the base, bigger the value, higher the pH or lower the pOH. And the main take-home is that the whole reason we did that thought process because we want an expression to figure out what is Kb. Well, we rearranged the equation on the previous page and we get this. But we have to make sure the Ka is for the conjugate acid to the base. So, for example, we are going to calculate the Kb for HC6H6O6. So, we go Kb is equal to Kw over Ka. So we know Kw 1.0 times 10 to the power negative 14. Now remember, this needs to be the ionization constant for the conjugate acid of this. So that means if HC6H6O6 is the base, then the conjugate acid is going to be, oh sorry, I forgot the negative, it's going to be H2C6H6O6 is the conjugate acid. So we need to search the Ka for this one right here. So we go to our data booklet and we try to find it. And of course, when you do your searching, you should find it. Hold on one second. I think it's on the next page. Here we go. So this right here, conjugate acid, right? Because this was our base, conjugate acid, so we use this value right here, 9.1 times 10 to the power negative 5. And we get 1.1 times 10 to the negative 10. And that is the Kb. Now, another thing that we can do is for our amphoteric or ampiprotic species. And that is actually determining if they should be acidic or basic, whether we put it in solution. So let's look at this. So calculate the Kb for HCO3. And then, of course, is the hydrogen carbonate acting as an acid or a base? Well, first thing for Kb, if we got HCO3 minus as the base, then the conjugate acid is when it picks up a hydrogen, it's going to be H2CO3. Okay, so if we go Kb is equal to Kw over Ka, our Kw is 1.0 times 10 to the power negative 14. Remember, the Ka is for H2CO3. So we go to our data booklet and we find H2CO3, which is on page 9. And H2CO3 is right here, right? Because this was the base we're dealing with, and this is the conjugate acid. So 4.5 times 10 to the power of negative 7. And we get a value of 2.2 times 10 to the power negative 8. Now, when we're asking this question here, is HCO3 minus acting as an acid or a base? So we got Kb, well that's almost wrote down Kd. We do not have Kd here. Kb, I don't know why that just turned black. Kb is equal to 2.2 times 10 to the negative 8. Now Ka Ka. Now remember, what we use right here, H2CO3, this is this 4.5 times 10 to the power negative 7. This is for H2CO3. If we're comparing if the hydrogen carbonate ion is going to act as an acid or base, well, we just figured out what the Kb was. What is its Ka? Now remember, our data book was filled with Ka ionization constant for acids. So when we find our hydrogen carbonate right here acting as an acid, well, this is the ionization constant, 4.7 times 10 to the power negative 11. Well, we can tell by comparing these right here, Kb is greater than Ka, so HCO3 minus act as a base. And that is one of the helpful things that we can get from these here. Now, of course, going through this, understanding what Kb means and being able to go through some of these steps, of course, will be handy, but now where yesterday's lessons, or the last lesson you just looked at, where we used our data booklet and we calculated pH and pOH, and we did a bunch of stuff just using the Ka values or evaluating for Ka, we're going to do the exact same things right now, except for Kb. So we can calculate Kb from given data using ice tables, or because now we have the tools to calculate Kb, we can predict the concentration of hydroxide ions when the initial concentration of the weak base is known, and the assumption check is still going to be the same for this one as it was with the acids. So nothing is really changing on how we're solving stuff, just our initial equation and how we solve our, and now it's just everything in the term of bases. So our calculations are going to be very, very, very similar from now on that you're going to notice. So first step, student measures a pH of 0.250 moles per liter solution of aqueous ammonia and finds it to be 11.32. So right away, the fact that we know this is a pH above 7, we should come to the conclusion that ammonia is a base. Therefore, because ammonia is a base, we got NH3, we need to show the base reaction. So that means this is a base, this is an acid. So we're getting this reaction. Now, same thing as before, you can develop your ice tables if you want to, but they're not really needed because, as we know, it's just a transfer of one proton and one proton only. So how we fill out our ice tables are the exact same as our acids. The only difference is that now, oh, sorry, I forgot the minus X there for E. And we have these right here. So if we knew the value of X, we can solve our expression, which we should know the value of X because we're given the pH. Now we do just have to be careful a little bit here, and that is, remember, when we get, you can either get the pOH and then solve, which that works as well, so if you want to do that, why not? Or you can get the concentration of hydronium and then find hydroxide using Kw. Either one's fine. So if you want to go pOH is equal to 14 minus pH, you can do that. And we get, so there's the pOH, and then concentration of hydroxide is 10 to the negative pOH. And when we do that, we get this. Of course, concentration of hydroxide, this is our X value, so we can put that inside of our Kb calculation. And I don't really have enough room to fill everything in, but when you do, you should get 1.8 times 10 to the negative 5. So remember, this is your x value here, and you plug this into x there, and then of course in your bottom, your 0.250 minus x, you plug that in down there as well, and you should get your kV of 1.80. Now for example 2, same thing, finding pH and pOH of baking soda, which is just sodium hydrogen carbonate. Now we've just done work on from example 2 that we know HCO3 minus is a base. If we didn't know that because we just done it, then you would need to figure everything out. But we kind of have the steps right here to solve for it, if need be, where we can write out the ionization equation. So we know it is a base, so HCO3 minus plus H2O, base and acid, so we know hydrogen goes over here, H2CO3, and then plus our OH minus. From this we know our equilibrium law, we got H2CO3 that is our equilibrium law. Of course we leave out water, and then we start going through the same stuff as well. Now, you'll notice in this example right here, pH is not given to us, right? Whereas the previous example it was. So this is where you do need to use the information that we are given. Now, luckily, we've already done the work back here on the previous page to find Kb for this particular example, which we solved for. Kb was 2.2 times 10 to the power negative 8. Now, if we didn't already do this work, we would need to, do the extra little bit for it. But we're just going to repeat this step right here to determine Kb from Ka because we're outlining all the steps for you. So remember, if HCO3 minus is my base, the conjugate acid is H2CO3, right? And the Ka for this one from your data booklets is the value of 4.5 times 10 to the negative 7. So we go Kb is equal to Kw over Ka. We got 1.0 times 10 to the negative 14 all over 4.5 times 10 to the negative 7. And we are left with 2.2 times 10 to the power negative 8. Now remember, when we were using our Ka to solve for acids, we needed to do this assumption check. Same thing for our bases. So once we have our Kb value, we do our assumption check. This is just off on the side. So we take the concentration of our base divided by Kb to see if this is greater than 1000. So in this case right here, our concentration of our base from reading the question was 1.20. Our Kb, we just solved for up there, was 2.2 times 10 to the negative 8. See if this is greater than 1000. And we do get a very, very, very large number. Sorry, that looks like a bunch of gibberish. We get 54545455. Is of course greater than 1000. Because the assumption check works, you will notice this equation looks very, very, very similar to the acid one. The only difference is we swapped out hydroxide for hydronium, we swapped out Kb for Kw, and we swapped out the concentration of the base instead of the concentration of the acid. And that is the beauty thing about this equation right here, is that it's interchangeable. The only difference is that we're using all of our hydroxide stuff instead of hydronium. And we plug our values in. In this case right here, we get 1.6 times 10 to the power negative 4. And once we know hydroxide, we can get POH is equal to negative log concentration of hydroxide, and you get an answer of 3.80. And to get pH, we go 14 minus POH, and we get 10.20. And solving for those S like we did with our acids. So you will notice that this is kind of the, not really the end, but there's not a lot of other examples on with this, because really, in essence, if you're able to get through the ionization constant for the acid, you will notice all the parallels here with the bases, right? The only difference is that you do need to do this step right here, that's step 3, to determine Ka from Kb. And of course, that's really it, the only different step, because writing at the ionization constant, once you realize something is a base, you write it your equilibrium law, highlighting that it's a base. You get Kb, because it's a base, you do your assumption check, and all you're doing is just swapping out hydroxide for hydronium, Kb for Ka, and of course the concentration of the base instead of the strong acid. And that is how we solve all of the base strength stuff. Now, I know that was kind of a lot there, but once again, practice makes perfect. There is some stuff there in your workbooks to kind of go through, but then we also have 2 diploma examples, or sorry, 3, using the whole idea of acid and base strength as well. All right. So if you want to try these on your own, please do. But if not, you can just pause the video and then just skip right to the end when I actually have the answers up here. But if not, I'm actually going to go through them with you as well, just so we're all on the same page. So just kind of reading right here, we got potassium sorbate. You know, honestly, you can read all that if you want to. I'm just going to jump right down here and actually figure out what I'm trying to solve for, and then pull information from the top question. That's honestly all the best way to answer diploma questions. So it says the value for Ka for sorbic acid, expressed in scientific notation, is A decimal B times 10 to the power negative C. Okay, so we're looking for Ka. Now, sorbic acid is not in our data booklet. So one of the things we have right here is, we have our Kb. So if this is the case, we know that Ka times Kb is equal to Kw. So if we rearrange this equation, we can get Ka is equal to Kw over Kb. And when we actually do this, so we get 1.0 times 10 to the negative 14 all over our 5.8 times 10 to the negative 10. We get a value of 1.7 times 10 to the power negative 5. That means this is our A, B, and C. So we got 1, 7, 5. And that is it. So nothing really spectacular about that. But it's just understanding that this was giving us a Kb, and also the hydroxide hanging around here was also kind of a huge hint that we're dealing with a base. All right, now for 37, the amount of sorbic acid present could be increased by. So this is a Le Chatelier's principles question. So remember, adding HCl is also the same thing as adding H3O+, because that is a strong acid. We add sodium hydroxide, we remove H2O, or we remove C5H7COO negative. So we're going to go through each one of these and figure out which way Le Chatelier's principle will push it. And of course, sorbic acid is this one right here, so we're trying to shift equilibrium to the right. So if we add HCl, so if we add an acid, one thing to notice here, we have a base. So if we add the acid, it's actually going to neutralize the base. It's going to decrease the concentration, which, remember, if we decrease, it shifts to the same side. So, hey, look, our first example, A is the correct answer. If we add NaOH, we increase the concentration of hydroxide, shifts to the opposite direction, not what we want. Remove H2O, when we remove, it shifts to the same side, not what we want. Same thing, removing our sorbate ion. If we remove it, it shifts to the same side, opposite way, not what we want. And finally, the last one, when reacted with our potassium sorbate, an acid that will produce an equilibrium that favors the reactants. So this one right here, this one's a little trickier. And the reason for that is that you have to remember we're looking that favors the reactants. So when we mix stuff together, if our strong acid is above our strong base, our products are favored. If our strong acid is below our strong base, reactants favored. So this question's asking for this scenario right here, where our strong base needs to be above our strong acid on our periodic table. Now the thing is, sorbic acid is not there, but from this value right here, we know Ka is equal to 1.7 times 10 to the power of negative 5. So we need to figure out if this is going to act as a base, and this is going to be the Ka for the conjugate acid, but either way we want it to fit inside of our book. We need to figure out, is it going to be above? So we're going to have to go to our data booklet. We're going to have to find our each one, so A, B, C, and D. So we have our HCOOH, C6H5COOH, C2H5COOH, and C2H5OCOOH. Not too much difference between these two right here, but how they're found in your data booklet, massively different. So let's find them in our data booklet. All right, so switching over to our data booklet, we find our first one, so our HCOOH here. And its Ka is 1.8 times 10 to the power negative 4. We have our other acid, another one, and the last one right here. So remember, we're looking for the combination of our strongest acid and our strong base. So it's safe to say that we see our propanoic acid, our C2H5COOH, is our weakest acid out of all the ones that are given. So based on this information, we should assume that if we have our strongest acid out of the 4 that's there, that one should give that particular scenario. So we choose C. So that is it for that one. So our last video is going to be interpreting pH curves. And then that will be it for this unit, and that will be it for Chem 30. So I know these last few lessons are a little long, but that's just kind of how they are. We can't really break it up just because there is so much that we need to cover with using Ka and Kb, but please go through the work for these here. The Ka and Kb calculations are definitely the more challenging portion of this unit, so you definitely want to try to master as much as you can. So work through your workbooks, work through all the problems if need be, and if you have any questions, make sure to email or come to the extra help on the Thursdays. All right, so see you guys for the last lesson of Chem 30.